Okay, let's start. So welcome to this third webinar for the ML4LM. And today's talk will also try to bridge the route between the physical and land modeling and the machine learning. And we would certainly benefit from the expertise of our speaker today, especially in global land and hydrological modeling, Professor Kei Yoshimura, who kindly accepted with a very short notice because this talk was meant to be done by Gab. I mean, this is a different talk, of course, but Gab had some unforeseen circumstances, and then Kei kindly accepted to give this talk. Kei is a professor at the University of Tokyo, currently serving as the director of Global Hydrological Center within the Institute of Industrial Science, and leading research on land modeling, early flood warning system, and climate reconstruction based on water isotope, which is not that usual for our field. And beside his numerous awards obtained in the field of hydrometeorology, Kei is also a member of the GeoX GHP panel. And he's also a member of the steering committee of the International Land Modeling Forum. He's also part of several observational based and model intercomparison projects such as the PIPS, SWING, and CEOP, which actually put him in a good position to disentangle which process are maybe more prone to be represented by machine learning. And with this, I give the floor to Kei. And just one comment, so please put your question to Kei on the Q&A section. Over to you, Kei. Thank you.
Thank you, Sohail. Good morning and good evening, everyone, and then maybe late evening. And well, my name is Kei Yoshimura, and I'm going to share the screen now. So, okay, again, hello, everyone. I'm going to talk about the machine learnings for terrestrial simulation this time. And then, well, as Sohail said, well, it's a very last minute for me, actually, and I was surprised. But well, this time it is really a great opportunity for me, and then to explain, introduce about our machine learning activities for the land simulations. So, well, thank you very much, Sohail, and thank you very much for those who are participating. And then also, I'm sorry that if you expect Gab's talk today, but well, please forgive me, and then please, well, listen to my talk instead. Anyway, so I have to first thank to my colleagues, Tomoko Nita, Takao Yoshikane, Gaohong In, Roman Olsen, Wenpeng Xie, Hongmei Li, and then Tami Mamin. And then they are mainly contributed to make the slide today. And then, well, let's start. And then, well, let me start with the typical terrestrial simulation framework. Well, and then as you all know, well, the land model is not only for the coupled with atmosphere, but we are using the offline, land model as an offline simulation, like a standalone model. And then on that case, we usually use, sorry in Japanese, but offline, atmospheric forcings, which includes precipitation, temperature, radiations, wind speed, and humidity, and so on. And also the boundary conditions, which is like a land type, soil type, topography, albedo, LAI, those kind of things too. And then we have a land surface model or a hydrological model. We sometimes use them combined. And then the final product is, well, depends on your study, but like a river discharge or soil moisture or snows, whatever. And then those are also depends on your purpose. Okay, then well, today's topic is the machine learning. So I'm going to introduce 5 different topics on how the machine learnings are used for the offline experiments of the land surface model or hydrological models. And then the first is the downscaling and the bias correction of the atmospheric forcing, which is a crucial data to drive the land surface land simulations. And then the machine learning to be used to improve the physical understanding. Actually, it is really the key issue, because the machine learning is often criticized. It is only the black box, and it wouldn't help our understanding. But nowadays, I think we are overcoming those issues. And then I'm going to introduce one of the such examples. And then the third one is the parameter calibrations. So, well, it was also introduced by the Dave's talk last time. But the parameter calibration is one of the, very important and essential parts. But it hasn't been well established. But because of the deep learning or such a machine learning technique, those computations or the optimization can be I mean doing better now. And also a speed up of calculation by using emulator, that is also covered by the Dave as well. But we are making the emulator of the land surface model as well. And then the fifth one is a little bit application. So by using the machine learning, the downscaling technique is application of downscaling technique, but something like terrestrial water storage, which is known as a very broad, low resolution information. However, how can we make the high resolution information can be made with the machine learning approach? So those are 5 topics which I have to finish soon. So okay, so dynamical downscaling. So to make the atmospheric forcing, we have to make the high resolution atmospheric information, and then it used to be we used to use something like dynamical downscaling, and of course it is still on use. But the dynamical downscaling is running a regional model, and then it was driven by the low-resolution global model. It is known to be a very heavy process. So, even though it is really good to make a fine-scale atmospheric conditions, but it is, computationally heavy. So the downscaling with AI is a kind of a reasonable solution. And then, it is actually one of the statistical downscaling. But by using AI, it is, like a super resolution technology has been, improved. And then as shown in this figure, so that the simulation, which is I'm typically 100 or 200 kilometer resolution globally, but by using AI, to train with the high resolution observation, the machine learning could make the more reasonable distribution with the high resolution. That is the idea. And then, it is very improved. Very established in the computer graphics. So we are using the characteristic that local weather strongly influenced by the broad area weather, and then by recognizing the pattern, the relationship between the high resolution and low resolution, so that we can make the high resolution, super resolution, by only using the low resolution inputs. So so this is the methodology, and then I will skip the detail, but it is already published by some papers. So the idea is only, I mean, let's make a high resolution observation and then low resolution simulation, then how to make the estimation in between. And then, as shown in here, it is a precipitation, and then precipitation, low resolution precipitation is nicely downscaled. And then the good point of this is even for these simulated simulated fields, it can be applied to make the realistic high resolution data. So the GCM data is used as a input. And then even though GCM is only, one of the realization, it's never be, realized. However, we can make the downscaled product from such a, realistic, but not real fields. So, by the way, we are using the some not the very deep learning technique, but the support vector machine is used. So the results is something like this. I mean, as I shown already, but the precipitation field, low resolution is resolved. And then the same technique can be applied for the other atmospheric fields like air temperature, wind speed, humidity, and so on. So radiations. So basically, by applying this technique, we can prepare all the variables of which is needed to simulate the land surface model offlinely. So, the scheme just continues, but the good point of this technique is that we apply the downscaling, super resolution for time slices, which means 6 hourly or 3 hourly or hourly. I mean, it depends on how you have input data prepared. But the accumulation of those input is, of course, called making an average, monthly average, or the climatological characteristics. For example, precipitation frequency or precipitation extreme. And then this is typically the improvement part, but the monthly average is, in this case, slightly underestimated. But the observation is lower panel, so our estimates from the GCM is showing much nicer pattern. And then the biggest improvement is into the extreme or the frequency. So those realistic patterns of the precipitation or other atmospheric field is indeed the benefits of using such a technique. Well, that is a historical period, but the benefit is also appeared in the climate future scenario as well. So this is actually hard to validate it, as you know. Because we cannot verify the future like 2050s. So in this case, we verify whether this bias correction, this downscaling technique can be fruitful for the climate change by using the latest 30-year and then old 30-year, past 30 years. So then what it is showing here is that for the right-hand side figure, we used climate simulation of recent 60 years. And then we assumed that there are climate change already happening, and then which is true. And then we compared with the observed field. So, and what it is shown here is the left hand side is the observation observed. So it's only limited area over Japan. But there are some sites or some tens of sites which have a longer than 60 years record. And then we could make an whether the climatological value is changing or not. So in this case, the top is the precipitation frequency, and then the monthly average, and then extreme, 99 percentile. And then there are some sites which are showing the increasing trend or decreasing trend, actually. But what is done in the AI is showing the range of the range. So that, of course, it is I mean, many ensemble results. So the alert scenario is making the lower I mean, the decreasing trend of the extreme precipitation or increasing trend. And then in average, it is, I mean, all showing the increasing trend. But the model simulation is extreme, I mean, underestimates such a volumes. I mean, the absolute value is much lower. But by using this technique of AI, then the increasing trend and also the absolute volume of the extreme precipitation is kind of similar to the what is observed. So was the frequency and so was I mean frequency and the monthly average. So this is the what somehow verifies, validates the whether this technique can be applied for the future climates. Of course, I mean, basically we cannot validate in like for the future in real case, but nowadays we can have some climate change already. So, this is an application to the hydrological. So one of the benefits of using the high resolution data is making a much better hydrological process. So this is GCM precipitation. It's I mean, very low resolution, but precipitation is now high resolution, so that the discharge is, I mean, by only using the same resolution hydrological model is used, but the results of that, I mean, discharge as a result is much different. Oh, this is just an example of the very local basin in Kyushu Island of Japan. That the detention curve of this discharge is becomes much realistic by using the higher resolution atmospheric forcing. So what is shown here is the how the daily discharge of this point exceeds 1,200 cubic meter per second, which is 95 percentile. But without dynamical downscaling, I mean the downscaling of the atmospheric data, actually it never appears in different atmospheric, different GCM simulations. However, by applying the AI downscaling, then the frequency are going to be similar to what is observed. Okay, so this is the first part. But now, from now on, I'm going to introduce different topics with a shorter period of time. But actually the same method can be applied for the uh, forecast as well. I mean, operational scale. And then the intra-seasonal to seasonal forecasting, S2S scales, which is also applicable. So, and then actually this one is initiated by the, WMO's activity of S2S AI Challenge, which has happened in 2021, I believe. So, well, at that time, actually, we couldn't make the good score. But later than that, Gao Hong In, who is now working in China, And then she's, well, she applies the same downscaling technique for the S2S precipitation and STS forecasted temperature. And then, well, figured out the bias corrected, downscaled product as a, better skill than the original one. So this is our correlation and KGE, and then root mean square and bias, and compare with the CPC precipitation. But well, it doesn't have a, like a 40 days lead predictability, but with this black line is showing the original ECMWF score, but having a, well, since we are using the observed fields to be trained, so well, our estimates are, make the, slightly improved for the all the scale metrics. And then which is actually good in terms of the ranking performance of the ensemble prediction. So, well, it's difficult to show, see. So please just focus on the this third column in the center. So this is showing the difference between the original RPSS, the ranking skill score, and our methods ranking skill score. And then green is better by our method. And then the pink is deteriorated. Well, there are some places which the ranking, the score is deteriorated. However, most of the case, there are green area. So what is showing here is actually the green area is corresponded to the blue area of the left-hand side. By the way, those figure is from starting from early period to the later period. It's week 1 to 6. So the top one is the weekly forecast. And then the most of the improvements were occurred in the blue area where the original ECMWF didn't have the very good predictability. So the point of the scheme is that, well, it doesn't deteriorate where the original score is good, but it improves the places where the original score is worse or bad. That is our finding. And so actually it is still undergoing, but done by my master student, Tamima Amin. She's trying to use this precipitation fields to the hydrological forecast. And then we are trying to investigate where the forecasted river discharge is is improved or not. Well, so far we cannot say where the improvement were occurred or not, but there are some good results so far. There are significant improvement. Okay, so next topic is how to improve the model. So this is a study done by my doctoral student, Honmei Lee, and then she's trying to improve the stomatal conductance, stomatal regulation. So stomatal regulation is very important, of course, to, well, estimate the transpiration or the photosynthesis. But and then there are many several models already introduced. But and then one of the physical model, plant physiology model is Medrin model. Proposed in 2017, and which is known as a very good model. But we tried, well, we applied a machine learning technique, based on the CDNN, convolutional deep neural network. And then, well, to make the story short, actually, it outperforms the physical model, which is actually happens to every field of the science. Well, the machine learning can be better than the what we thought it is good. But why is our question? So, well, so let me introduce this one. This is just a skill score. And then the what we understood is when we give us the input variable, so BPD, I mean humidity and CO2, and then soil moisture and like temperature. So those are the, different parameters given to the machine learning model. And then of course, the more the input variables is given, the skill tends to be better. However, there's some over limit, an upper limit. So the experiment 4, which we inputted delta T, which is the difference between leaf temperature and air temperature. When we input this delta T, then the machine learning score is becomes, the highest, or the hit the plateau. So, well, we understood that the delta T, the difference between T leaf and the air temperature, is it's the key parameter to estimate the stomatal conductance better. And then, but the original Medrin model or other like a ball belly type, or other stomatoconductance model actually didn't use the delta T, the difference between T leaf and the air temperature directly. And then we investigated which range of delta T the model, physical model performs worse, and then the machine learning performs better. And then we figured out there are some certain range where the delta T is, well, smaller than 0, which means that leaf temperature is lower than the air temperature. In that case, the Medrin model performs not good. So and then this is well, the explainable machine learning results. So this is accumulated local effect is shown. So well, I don't have time to explain it in detail, but well, what it indicates is that so the color is showing the contribution to the stomatal conductance, and then the horizontal axis and vertical axis is always delta T. So that the relationship between the delta T, temperature difference, and the other parameters are showing like this, and then how it is impacted to the stomatal conductance is shown. And then what is understood from the machine learning approach is that this relationship is changing by the environmental conditions. So, and then we already know that this change depends on the environmental condition has not been fully implemented in the physical model, like a Medrin model. So we haven't done the real improvement of the the physical model, but machine learning definitely could give us some hints to where we should make an improvements, or we should revise the physical model. So, and the other topic for the application of the machine learning is calibration. So calibration of model parameters using a deep learning technology is done by Wenpeng Xie, who is working as a postdoc in our lab. So well, in that case, we make a foundation surrogate model. So the surrogate model is a kind of a replacement of the physical model. So try to imitate the physical model is the first step. So like it can be called as an emulator. But by using making such a surrogate model, then well, we can tune the the parameters which are embedded in the physical model. So in this case, we use the Matsushiro model, which is known as one of the popular land surface model developed in Japan. And then we made a foundation surrogate model of Matsushiro, and then we've done the calibration optimization by using the Plummer 2 data. So there are many Plummer 2 sites, and then we picked up several, 4 land type, the vegetation types, plant functioning type. And then the period was chosen with the criterion of the full data sets are available. So those are the sites we picked up. There are a little bit more than 20 sites. And then, first we made a training, the surrogate model, and then trained the surrogate model, and then we optimized the parameter using this technique called DPL, the differential parameter learning scheme. And then I'm also skipping the detail, but the result is shown here. So this is the results for the all averaged score of these Plummer 2 sites. And then root mean square error is shown. So the higher is, lower is better. And then we compared with some other models results. And then the ILS DPL is our calibrated results. And then the ILS ORI is the original results. And then the other models. And then the SFE is, the totally different, not the land surface model, but more like a diagnostic scheme to estimate the sensible and latent heats. So by the way, this is the root mean square error for latent heat, and then with a different time resolution. So we wanted to know how the parameter optimization worked in different time scales as well. So from 30 minutes to annual average is shown here. And then, fortunately, we made this calibration worked nicely, meaning that the pink is the original and then green is the calibrated. So there are root mean square error decrease, which means, just good. But compared to the other scheme, we compared with LSTM estimates as well, which is one of the participants for the Plummer 2. But actually, before that, the original model couldn't outperform the LSTM. But actually, we are using the deep learning technique, but we could make the parameters optimized for those sites. And then now it exceeds the performance of LSTM in the all time scales. So similar results has been obtained in the, for example, sensible heat. And so this is the results for the calibration using the machine learning. And then, of course, it is site simulation, but how to apply for the global scale is another interesting topic, but we don't have clear direction yet. So right now we have been, I'm trying to introduce how to use the machine learning technique for the atmospheric forcing and the land model improvements. But land model itself is slow. It is much faster compared to the atmospheric model, but it tends to be, computationally heavy. nowadays. So, well, how to reduce the computational load is also, I mean, very important topic. So, well, we are using trying to make the emulator for Matsushiro, which is our land surface model, for this purpose. Trying to reduce the computational load. And then, which is done by Roman Olson, who is also our researcher in our group. And then he's made a nice emulator. So I'm going to introduce. So in this case, it is not a deep learning, or actually it's not even a machine learning, but we simplified a physical process which was embedded in a Matsushiro model. So, well, actually, he found out what is done in the Matsushiro. Based on the Richard's equations or many physical processes. But as a result, actually, those processes can be simplified into some, I mean, uh, equations like this. So the first snow storage, and then water flux, soil moisture process, and then wetland coverage change, and the river runoff process. Those are all simplified equations. And then incorporate the additional parameters, which is dedicated to this emulator. So what is used in the land surface model, original model, is no longer used for the emulator. And then the optimization of the emulator parameter, which is different from the calibration topic, by the way. So these 14 or 15 parameters are independently tuned. So the parameter optimization has been done. So, we put lots of efforts to how to make the optimized parameter sets for the emulator. And then, the results is, we conducted more than 100-year simulation of Matsushiro first, and then we are trying to make that the emulator to imitate the results. And then the right-hand side is showing that how the imitation is good. So the snow or wetland storage, upper layer soil moisture or runoffs are shown. And then, there are some differences, but as a snapshot, it gives very similar results each other. So the emulator performs good. But what is most remarkable by using emulator is the computational load. And then what was originally done by the Matsushiro model was more than 20 minutes, but by using the emulator with 36 processes, it becomes less than 1 second. Of course, it excludes the all I/O, but where the Matsushiro includes the I/O process. So it's not a fair comparison, but I was surprised to see such a, reduce such a computational cost drastically. So, and then, the performance was already well verified. And then we found out the training period doesn't have to be 100 years, but a little bit more than 20, 10 years or 20 years is enough. So, this is our conclusion in this case, by using this emulator. So it is already published in 2024. And then now Roman is making this emulator embedded to our land surface modeling system, which is called Integrated Land Simulator. So Integrated Land Simulator consists of land model and then hydrological model. So the Matsushiro is our land model, and then which was computationally heavy, but it's consists of physical schemes. But now we developed the emulator for Matsushiro. So instead of using the physical model, why don't we use the emulator, and how it performs as like land surface processes is what we have done recently. So, well, in this case, actually, this emulator has been improved for like base flow or numerical scheme, and then the global parameter optimizations using the differential evolution. So basically, the emulator, performed better. Well, the result is something like this. And then now, not only the land parameter, like snows or soil moistures, but the runoff generated from the emulator or the land surface model is given to the hydrological model to simulate the discharge, river discharge. So the river discharge is shown here as a metric of how the emulator performs nicely. And then these are the different basins. And then the river discharge of Amazon, Brahmaputra, Lena, those are almost the same. Blue and the red lines are showing almost the same, which means emulator performs as just same as the physical model. And then the left-hand side is a snapshot of flood fraction, which is almost the same here. And then the computation is, of course, the key. And then in this case, because we embedded the old emulator into the system, so it is indeed a fair comparison. And then with this fair comparison, including I/O, and then we found out where the original model takes more than 20 minutes, nearly 30 minutes, but it can be as good as like 100, little bit less than 200 seconds. And then by considering the volume of the computation nodes, the speed up of 30 times has been achieved. So, well, which is good news that we can increase the resolution, or we can increase the ensemble members with the same amount of computations power for the future use by using emulator instead of physical model. Okay, so I have to finish, but one more topic is remaining. So, well, the last one is that the downscaling of terrestrial water storage. So the GRACE is unique satellites which can observe the groundwater volume, but anomalies, but those are low resolution. So can we downscale that such terrestrial water storage into final resolution? Is the one question. And then can the downscale TWSA, anomaly of the terrestrial water storage, better capture the water mass variation of sub-regional to local scale. And then can it be a proxy of flood and drought monitoring? That is our questions. And then this was done by Gao Hong Ing, and then it is just published. Accepted just a few days ago. So okay, so I have to skip the parts, but what we are trying to do is using GRACE as like a truth. So and then how can we downscale the GRACE? GRACE is low resolution data. So we are using the like a assimilated product of LDAS as another good information source. And then to make it operationally used, we are using today's Earth product, which is our operational simulation results. So, well, to make the story short, well, first we made a synthetic simulation, synthetic experiment. So in that case, we are trying to show this scheme works as intended. So the truth has been made from the synthetic data, and then we tried to downscale the products of to be the same as the synthetic one. But we applied for the same technique to the real case. So in that case, GRACE data is, low resolution data is used to downscale the TWSA. And then we are trying to compare with the other information like a drought or flood metrics, which is independently observed from the other group. So, okay, so synthetic the results, let me skip this part. But the real world experiment results is actually, nice because the TWSA is something like this, and then the original data of grace is shown in black, and then our estimates of LSTM is showing in red. But here, by the way, this is a Texas case, and then some region of or partial part of the region in Texas is shown. Sorry, I forgot to put the map here. But the bottom figure is showing the drought index observed by the USDA, and then there are significant drought here in 2012, but not that big as the rest of the period. But the black line is showing almost the same range. But by using LSTM, red line is showing slightly milder drought conditions in the other years compared to the 2012. So obviously, the LSTM deep learning could improve the drought monitoring as well. Same for this is a part of Texas, and then we divided into different regions. And then, this is also particular. So the input, the black is grace, and then our estimate is red, and then the NORS data is blue. So where we observe the droughts, actually the TWSA is getting smaller. And then in this case, almost same drought severity from 2012 to 2015. And then in this case, red and black is pretty same. However, in this case, as shown before, but that only this 2012 is showing very severe drought, but the rest of the period is rather milder, whereas grace is showing a very severe conditions. So, and then we can apply the same TWSA, estimated TWSA for the flood monitoring as well. So, the flood potential index is obtained from the different data. So, I'm going to skip. But in short, the NCEI, which is the index of flood, and then it is showing red. And then the original grace doesn't show a flood. The positive anomaly in the northern parts, but the LSTM has shown, has detected some degree of the heavier, higher anomaly of the, which can be regarded as a flood in the northern parts. Whereas TE or NOR is showing the somehow different index, different indications. Well, and then we are estimating how the LSTM is good or bad compared to the observations. Which is the NSCE and NCEI. So it's not always good. However, we found out the LSTM is basically giving a positive impact. So meaning that either grace only or the land model only, but LSTM is a kind of combination of those two. So which gives a better signature and better information towards to the society. That is our understanding, and also it is pretty reasonable compared to the single source information. But well, I mean, how to combine the two independent information, and then we can make some sort of better results. So, well, okay, so this is it. So, sorry to be long, but well, this is just a summary. And then I introduced 5 topics. So, well, and then those are some of the results are still unpublished, but there are some published results as well. So please refer them if you like. Thank you very much.
Thank you very much, Kei, for this comprehensive overview of the activity with machine learning in your laboratory. And there are a few questions in the QA, and please input your question there if you want, or even raise your hand eventually, and I can give you the floor.
Okay, so a question from Matthias. In case of the stomatal conductance, what is VPD for you? It should be corrected to leaf temperature, i.e. ESAT tea leaf, and well, saturated evaporation, saturated vapor pressure of tea leaf, and minus E saturated saturated vapor pressure of the tea air. So perhaps this is why delta T becomes important. Yes, actually, this is a very, very significant point, and then we are trying to figure out. But one thing we are sure is the current usage of VPD in the Medrin model, for example, is form of root. I mean, root of VPD, and then well, it does not allow any negative value, and so that is a critical point of the Quora performance of the estimation of stomatal conductance. That is our belief. And then, well, I mean, machine learning actually doesn't care the physical meaning of VPD or so. So, well, I don't know if it is answers to your question, but well, this is the answer I can make so far. And then Awel Haji Ibrahim gave me, can you share the material with us, please? Thanks for good experience. Thank you very much. And then Sohail will put my input to the direct site sooner, I think. So thank you. Mohammed Amjad asked me, do you think these simulations using emulators can be performed for other regions easily? If yes, how can we collaborate? Yes, this is also a great point. And then, well, I mean, emulator, you need to train the model. And well, basically you have to perform the physical model experiment first. However, I don't think we need to do it for all the regions, I mean, all the time. For example, like once you learned it, like, well, here, I mean, in Tokyo, I mean, it is highly likely to be adapted to the different place like Yokohama. Well, Yokohama and Tokyo is quite far, but well, only a few kilometers, or similar land type, similar topography. Definitely, I think it can be applied. Only the difference is the atmospheric forcing. So, well, that is another, I mean, interesting study can be made. And then, well, this is definitely doable. Well, I mean, once you have to do, I mean, once what you have to have is the high resolution experiment first, and then check if how many, how many grids you have to train the emulator, and then you can check if this emulator trained at a different point can be applied to the different grid also. So this can be done. And how much can we do is different, can be estimated. Fixing one asked me which machine learning algorithm is used for downscaling for the first topic. Okay, so I skipped that, but the support vector machine or support vector regression has been used. Sorry for skipping the explanation. But please refer the paper. And then, well, actually, you might be asking, well, this is known as a very old-fashioned machine learning rather than the deep learning technique, which is more popular nowadays. However, what we found out is that, well, support vector machine is still quite useful. And also, well, deep learning, well, we can try, but well, there are pros and cons, but definitely using deep learning technique is, can be made. But well, I also forgot to mention, but because support vector machine is simple, we can understand and then we can, well, similar to what is shown in the physical model improvement, but we can enlarge the feature vector region, larger or smaller regions, and then how much the local phenomena can be, well, influenced by the large scale feature. So that kind of, well, sensitivity can be studied by using support vector machine, which is perhaps harder for the using deep learning technique. And then well, last question, well, Haji Ibrahim again. Can it is possible to use such type downscaling GFS data by AI? I don't know. Well, which downscaling? Well, if you mean that GFS as atmospheric data to be downscaled to the higher resolution, definitely possible. So what actually, it is hard to explain why we can do, but once you learn and once you train the machine learning model with, for example, reanalysis, low resolution reanalysis and high resolution observation fields, what we understood is this trained model, trained feature vector can be applied to the modeled precipitation. So, well, it's no longer reanalysis or that, it's a future climate too. But actually it can be applied for different models precipitation. So we applied same feature vector to MyRock produced precipitation or ECAM produced precipitation. Actually, all of the precipitations estimated by the different models, but we have got not a similar, but there are, tendency of the future, climate model is kept. The characteristic is kept, but well, the downscaled, so the super resolution has been made. If the large scale feature from the global model is wrong, it is wrong, still wrong. But the fine resolution of this wrong field is obtained. You know what I mean? So GFS is good model. So I think the downscaling is definitely applicable. This is my answer. So thank you very much for the great lots of questions.
Thank you, Kei. I have one small question.
Yes, please.
The process understanding case that you made, it was on a forest, on a pine tree, I think.
Yes.
Did you try this on other type of vegetation like crops or grass? Because the canopy conductance might behave.
Yes, it's actually this is definitely a further study. We haven't tried many plant functional type yet. So I mean, what I showed, sorry, I mean, I missed the explanation, but well, it is only for the case of the, I mean, deciduous forest. I forgot. I mean, well, I mean, some forest type too.
Okay, and the last one for me as well is the emulator, the physical-based emulator that you have. I see that it is mostly based on hydrological focus on hydrological parameter. Are you planning to extend it to other parameter like the heat and sensible heat?
That's actually a very good question too. So well, we have to give up some feature. So in this case, I mean, our our goal to create the physical-based emulator is trying to make the hydrological process faster. I mean, hydrological estimates faster. So, but if your focus is, for example, to produce the latent heat or sensible heat right towards to the atmosphere, definitely we have to design different, I mean, well, the emulator. I mean, the framework can be different, but well, I'm saying, I mean, it's difficult to say, but the framework can be same, but well, we need to have different equations to estimate the sensible heat or latent heat. And then, so in this regard, we are not aiming to use the emulator as a replacement of land surface model in the ESM. We are not thinking about it, but well, only for the offline purpose, I think it is useful for now. Yes.
Thank you very much, Kei, and yeah, it was an honor to have you, and then see you all for the next webinar. See you.
Thank you very much.
Bye.